Kia ora team, this is Mr. Dharma, and today I want to talk to you about optimization. Optimization is the fancy way of saying finding the local minimum or the local maximum. So consider this example. There is a bridge whose height is measured in meters, and it's given by this equation. Negative x times x minus 8. Okay, so x is distance in meters, and h is height above the ground, also in meters. So let's draw a picture. So we've got one intercept at 0 and the other intercept at 8. Okay, and it's a negative parabola. We can, based on the algebra that we know that the turning point is going to be at 4. But let's try to use calculus to determine that and find out that that is the optimal point. So how do we do that? Well, we take our function and we expand. So that's negative x squared plus 8x. And so once we've expanded, we need to find when the gradient is 0. So we differentiate. So we multiply by the power, take 1 off the power, multiply by the power, take 1 off the power. And so I want to set that equal to 0 and solve for x. So x is equal to 8 divided by 2, which is 4. Which is exactly what we predict because we know about parabolas. But it's good to use calculus. We're in calculus. Now I'm going to substitute x equals 4 into the height equation. Negative 4 squared plus 8 times 4, negative 16 plus 32. The height is 16 meters. So the tallest point of the bridge is 16 meters tall, and that happens when x equals 4. Does that kind of make sense? So we've optimized for that turning point. It is the same as finding the stationary point maximum minimum, but now we're doing it with context. So to find an optimal point, you differentiate, you set it equal to 0, solve for those x values, and substitute those back in. You might need to check using the second derivative test whether it's a maximum or a minimum, but the point is optimization is just differentiating, setting equal to 0, and solving for x. I hope that makes some sense to you. There's optimization questions that can get a little trickier. That's where you have to form the equation that links the two variables together and then carry on. So let's do another example. Consider I want to make the largest rectangle possible and I've only got 100 meters of fencing. So the largest rectangle I can make will be this. Remember, squares are also rectangles, right? So I have an x dimension and a y dimension. What do I know about these things? I know that the perimeter is going to be 2x plus 2y, and I know the area is going to be x times y. But I've only got 100 meters of fencing, meaning the perimeter is equal to 100 meters. So that then means that 2x plus 2y equals 100. So can I form a relationship because I'm trying to optimize the area? Yes, I can. So what I'm going to do is I'm going to make y the subject of this. 100 minus 2x, and so y is equal to divide everything by 2, 50 minus x. So I have an equation for the area, x times y, and now because of this perimeter that linked them together, I now have an equation for the area that is x minus 50. Notice it's very similar to the question before, and if I want to optimize it, I need to find the gradient and set it equal to 0 and find out when that happens. But before I can differentiate this, I need to expand. So I get 50x minus x squared, and so that is the area, and so to differentiate, dA by dx, multiply by the power, take 1 off the power, multiply by the power, take 1 off the power. Remember, the optimal point happens when the gradient is 0. Solving for x gives me x is equal to 25. Now that I've got x equals 25, can I find the maximum possible area? Yes, I can. Because x is 25 meters, because x is 25 meters, and y is equal to 50 minus 25, y is also equal to 25 meters. The area is equal to 25 times 25, which is 625 square meters, and that is the maximum. Okay, and I've plugged that into this area equation, but you could have plugged it into any area equation and you would have found the maximum. I hope that helps. Now you can use this strategy to apply to even harder problems. Now you might have cubics and stranger algebraic equations to maximize, but this is the main idea. Awesome. All the best, Mr. Dharma.